Good morning, children. Today in this video we will be discussing about abnormal molecular mass. So what is abnormal molecular mass? Suppose we have a solution acetic acid in benzene. So acetic acid is a solute here and benzene is the solvent here. So the structure of acetic acid is CH3, single bond C, double bond O, single bond OH, and because of oxygen more electronegative than carbon, oxygen will have slight negative charge on over it, carbon slight positive charge, here O has slight negative charge and H has slight positive charge. So what happens with acetic acid in benzene? So you see here in the next diagram, I have two acetic acid molecule, and because of this polarity, there will be a hydrogen bond formed. So two molecules of acetic acid has joined together, has associated together and formed a species which is called dimer. It's called dimer. Now children, you are well aware that the application of Colli-Giddy property is in determining the molecular mass of unknown solute. So suppose acetic acid in benzene, though acetic acid is a known solute, its molecular mass, if you calculate molecular mass of acetic acid, it comes out to be 60. Molecular mass of acetic acid is 60. So any Colli-Giddy property you use, for example, relative lowering in vapor pressure or elevation in boiling point or depression in freezing point or osmotic pressure measurement should give us value of 60 for acetic acid. But surprisingly, what we see is that the molecular mass of acetic acid in benzene, when we determine using Colli-Giddy property, the value comes out to be 120. Value comes out to be 120. It should have been 60, but it comes out to be 120, and that's why we call it abnormal molar mass. Abnormal molar mass. So question arises, what is the cause of this abnormal molar mass? And the cause of abnormal molar mass is right in front of you. It is because, as you have seen here, acetic acid in benzene doesn't exist in this form. Acetic acid in benzene exists in the form of dimer. So when you have acetic acid in benzene, it is this particle which is present in the solution. This is the effective particle. Dimer is the effective particle. So naturally, when we determine molecular mass through Colli-Giddy property, we will get the molecular mass of this particle. And it is because of this reason, we get molecular mass of acetic acid to be 120. Truly speaking, the molecular mass 120 that we are getting, is not abnormal, because it is this particle existing in the solution, and if this particle is existing in the solution, we will get the molecular mass of this particle, and that's why we are getting what? 120. Anyway, this we call it as abnormal molar mass. So The reason for abnormal molar mass is association of solute. Let me write it down here. Association of solute particles. Association of solute particles. Now let me give you another example of a solution. Suppose we have another solution, sodium chloride in water. Sodium chloride in water. So sodium chloride is a solute here. Now, calculated or theoretical molecular mass of sodium chloride, it is 23 plus 35.5, that is 58.5. So when we use colligative property to determine the molecular mass of NaCl in water, we expect 58.5 to be the molecular mass of NaCl. But surprisingly, in this case, the value that we get, it is nearly equal to 29, almost half of this value. So this is again a case of abnormal molar mass. So we have to find out what is the reason for this abnormal molar mass. It is very easy to find out the reason. NaCl is an ionic compound. It breaks down into Na plus and Cl minus. NaCl breaks down as NH plus and Cl minus. So in solution, NaCl is not existing. What is existing in the solution is this particle and this particle. This particle and this particle. And we will get molecular mass of this particle or this particle, and we get average value of this particle and this particle, and the average of mass of this particle and this particle will quite naturally be very nearly equal to 29, half of 58.5. So that is the reason why we get 29, nearly 29 as molecular mass of NaCl dissolved in water from colligative property. That means if here the abnormal molar mass was due to association of solid particles, then in this case it is due to what? It is due to dissociation of solid particles. Dissociation of solute particles. So we can say that if there occurs association or dissociation of solute particles in the solution, then we will get abnormal molecular mass. If there is no association or dissociation, then we will get the correct or the expected molecular mass. So one thing, there should not be association of solute particles, there should not be dissociation of solute particles taking place in the solution when we determine the molecular mass of unknown solute. Okay, now it was a scientist of the name of Van 't Hoff. He introduced a factor here, okay, and that is Van 't Hoff factor I. So if in exam if you are asked what is Van 't Hoff factor I, Van 't Hoff factor I is defined as normal molar mass divided by abnormal molar mass. Normal molar mass or abnormal molar mass. This is the definition of Van 't Hoff factor I. Normal molar mass we can call it as calculated or theoretical, and abnormal molar mass we can call it as experimental or observed. So if I ask you, what is the value of Van 't Hoff factor I for acetic acid in benzene? So for acetic acid in benzene, the value of Van 't Hoff factor I is 60 by 120, that is 0.5. If I ask you what is the value of Van 't Hoff factor I for NaCl in water, so for NaCl in water, normal molar mass is 58.5, abnormal molar mass is 29, so the value comes out to be almost equal to 2. So Van 't Hoff factor for NaCl in water, it is 2. So Van 't Hoff factor value can be more than 1, can be less than 1, or it can also be equal to 1. The value of Van 't Hoff factor I becomes greater than 1 if there is dissociation, of solute. The Van 't Hoff factor I becomes less than 1 for association of solute, and Van 't Hoff factor I will be equal to 1 when for no association or dissociation. So now one thing, children, you are quite aware from the expression for molecular mass of solute in terms of colligative properties, that molar mass and value of colligative property, are inversely related. This is very important thing you have to remember. Molar mass and value of colligative property are inversely related. So since they are inversely related, we can have another expression for Van 't Hoff factor I. That is, we can write, since in the denominator is abnormal, so it will be abnormal value of colligative property divided by normal value of colligative property. This also we can write. So this is Van 't Hoff factor in terms of molar mass. We can also write Van 't Hoff factor in terms of value of colligative property. As I already said, abnormal means experimental or observed, and normal means theoretical or calculated. Okay, so from here what we get is, you can see abnormal value of colligative property. Abnormal value of colligative property will be I times normal value of colligative property. Now suppose we talk about say elevation. Suppose we talk about elevation in boiling point. We talk about elevation in boiling point. We know that elevation in boiling point is represented as delta Tb. Delta Tb is equal to kBm. This we have already discussed. Delta Tb is equal to kBm. Kb is called molar ebullistopic constant and m is the molality of the solution. So this is theoretical or calculated or normal. So we can write for normal value, we can write this expression. So I into Kb into m. So abnormal colligative property, suppose this is we are talking about delta Tb. So delta Tb observed or experimental is equal to I kBm. That means if it is said in the question while solving numerical that there is association taking place or dissociation taking place, then you cannot use this relation. The relation that you have to take is delta Tb is equal to I into Kb into m. This relation you have to take. That means the relation gets modified. Similarly, if you are talking about depression in freezing point, so it will be delta Tf observed will be I Kfm. If you are talking of osmotic pressure, it will be pi observed is equal to I CRT. If you are talking about relative lowering in vapor pressure, then it will be delta P by PA naught is equal to, normally it is chi B, so it will be I times chi B. So children, this one, and this one. These are the modified relation, okay, of colligative property. If it is said that there occurs association or dissociation of solute in the solution. Now, let me talk about what are the values of I for different solutes. Let me talk about that. I already have said you the value for I in case of acetic acid. I already said you the value of I in case of sodium chloride. Let me talk about some other substance. Say K2SO4 potassium sulfate in water. Potassium sulfate in water. It is an ionic compound, so potassium sulfate, it will break down into 2K plus SO4 2 minus. So how many particles are being formed? 3 particles, 2 and 1, 3 particles. So for potassium sulfate in water, the value of I will be 3. Suppose this question comes in exam with this potassium ferrocyanide. Potassium ferrocyanide K4FeCl6. This is a complex compound. You will study about complex compound in the last chapter of part 1 book, last chapter of your part 1 book. Now this complex compound, in water, it breaks down as 4K plus FeCN4 4 minus. So potassium ferrocyanide breaks down like this, and how many particles are formed after dissociation here? 4 plus 1. This is a 1 particle, so it is 5 particles. So the value of Van't factor I is 5. But children, let me tell you one thing is, this value of I that we are writing it here, this happens if there is total or complete dissociation. Okay, total dissociation or association. But if it is said in the question that it is not totally dissociated, it is not totally associated, then the value of I will not be like this. Value of I will be slightly different from these values. Okay, I am showing you with an example. Suppose it is said in the question that K4FeCN, its formula is not FeCN4, it is FeCN6. Suppose it is said in the question that K4FeCN6 is 50% dissociated. 50% dissociated. So all compounds or molecules, they are not dissociating. 50% is dissociated. So in that case, the value of I will not be 5. If it is 100% dissociated, the value of I will be 5. So if it is not 100% dissociated, how do we get the value? So in that case, you have to remember this relation. Alpha is equal to I minus 1 divided by M minus 1. This relation will help you to determine. Now, what are these terms? Alpha is, degree of dissociation or association, whatever the case may be. So this relation, this relation is specifically for dissociation. This relation is for dissociation. So alpha is the fraction of dissociation. Suppose if it is 50%, as I say, then alpha value will be 50 by 100. Alpha value will be 50 by 100. And as you already know, I is Van't factor. Now, and what is M? Don't get confused. Here, M is not molality of the solution. Here, what is M? M is number of particles it is getting dissociated. What is the number of particles it is getting dissociated? So, for this case, the value of M is 5. Value of M will be 5. So let us calculate the value of I for K4FeCN6 if it is 50% dissociated. So as I said, we will start from here. So 50% means 50 by 100 is equal to I minus 1. We don't know the value of I. We are trying to find the value of I. And M value, like it is 5. It is breaking down into 5 particles. So 5 minus 1. So after that, what we get is here it will be 0.5 is equal to I minus 1 by 4. Next it will be I minus 1 equal to 2, and so I will be equal to 2 plus 1, that is 3. So children, you see, if K4 FeCN6 is 50% dissociated, then the value of Van't-Hoff factor is 3. If it is 100% dissociated, the value of Van't-Hoff factor will be 5. And if it is said in the question there is association taking place, then you should be using this relation: alpha is equal to I minus 1 divided by 1 by m minus 1. 1 by m minus 1. For example, suppose there is a solute. Such that 4 particles are joining together. 4 particles are associating together to form a tetramer. So in that case, we will write here 1 by 4. 1 by 4. If 2 particles are joining to form a single particle, that is, if there is a dimer formation, then we will write here 1 by 2. 1 by 2. If suppose there is a case where 5 particles are joining together to form a single particle, then we will write here 1 by 5. So for association, we will use this relation and we will get the value of Van't-Hoff factor I. So we will get the Van't-Hoff factor I, and then we will be using the modified equation of colligative property. For example, delta Tb is equal to I kbm, and we will get the experimental or observed value of the colligative property. Now children, in the next video we will be doing some numericals on Van't-Hoff factor. Numericals where Van't-Hoff factor are involved, very important. Till then, bye bye and have a good day.